We will now look at some applications to calculus of variations. Calculus of variations can be thought of as doing maxima minima in infinite dimensional spaces. Okay, so we are going to prove the following proposition. V reflexive Banach space and K contained in V a non-empty closed convex subset. Let phi from K to R, I am working with V as a real Banach space, okay, and be a convex and lower semi-continuous functional. Assume that limit as norm x tends to infinity of phi of x is plus infinity. So this is called the coercivity property. Okay, then phi attains a minimum on K. That means there exists a point which is the minimum value of phi and it's in K. Okay, so proof. So fix some x naught in K and let lambda equals phi of x naught less than infinity. So it could be some finite number. And you define K tilde equals set of all x in K such that phi x is less than or equal to lambda naught. So this is non-empty because x naught is already in that set. Okay, so we are having that phi is lower semi-continuous, therefore K tilde is closed. Then phi is convex, so this implies that K tilde is also convex. Then coercivity implies, of course, that phi is bounded. Sorry, K tilde is bounded. Because if you have an unbounded sequence inside K tilde, then the norm of phi of x should go to plus infinity, whereas you know phi of x is less than or equal to lambda naught. Okay, so you have all these properties. So let xn be a minimizing sequence in K tilde. So what does it mean? So xn belongs to K tilde for all n, and phi of xn converges to inf of phi of x in K tilde. So that is such a sequence exists always because you are taking the infimum. You can always find a sequence which goes to the infimum, and such a sequence is called a minimizing sequence. So K tilde bounded implies xn is bounded. Now V is reflexive, and therefore you have we have shown that any bounded sequence has a weakly convergent subsequence. So x and k which converges to x. So there exists a weakly convergent subsequence. Okay, so now because K is closed, K tilde sorry is closed and convex, this implies weakly closed, and therefore this implies that X belongs to K tilde. So inf of phi y, y in K tilde is less than or equal to phi of X, because X is in K tilde, and phi is lower semi-continuous, and also phi is convex and lower semi-continuous implies weakly lower semi-continuous. We have seen this also, and therefore since Xn converges to X weakly, one of the characterizations, one of the properties of a lower semi-continuous function is this is less than or equal to lim inf n tending to k tending to infinity phi of X and K. And of course but we know phi of X and K converges to the minimum, so this is limit, in fact it's equal to the limit, so this is equal to inf y in K tilde phi of y. So all of them are equal, so we have phi x equals inf phi of y, y in K tilde, and if y belongs to K minus K tilde, then we have phi y, and this is of course less than or equal to lambda naught, because all of the K tilde is set of all X which is such an phi y is bigger than lambda naught, and therefore we have that phi x is in fact equal to the inf of phi y, but y belonging to K, all the entire set. Okay, so that proves the theorem. So existence of a minimum is there. Okay, so so what does this theorem say? A coercive lower semi-continuous convex functional defined on a non-empty closed convex set of a reflexive Banach space always attains its minimum. Okay, so the remark, if K is itself bounded, we can avoid the hypothesis, avoid the coercivity hypothesis. So we now prove a theorem which is a direct consequence of this, and it's a fairly important theorem. So let V be a reflexive Banach space and K a closed, K contained in V, non-empty closed convex subset. Then for every X in V, there exists a Y in K such that norm of X minus Y equals the minimum of norm of X minus Z, Z in K. And if V is uniformly convex, then such a Y is unique. So you take the function phi of Z equals norm of X minus Z. So this is clearly coercive, it is convex and weakly lower semi-continuous. It is lower semi-continuous, it's continuous and then it is convex, so it is weakly lower semi-continuous. We have already seen this property of the norm. Okay, and therefore existence of Y follows immediately from the previous proposition. So in the previous proposition we said phi is lower semi-continuous and convex, and therefore it was weakly lower semi-continuous. Here we have phi is in fact continuous and convex, and therefore it is weakly lower semi-continuous by that property. So that is, and it's a weak lower semi-continuity which is important. You don't need other, in fact weakly sequentially lower semi-continuous. That means it is enough if for sequences you have that if xn converges to x, then phi of x is less than or equal to lim inf of phi of xn. That is called sequential lower semi-continuity, and that even is enough. In a metric space, that is equivalent to lower semi-continuity. In a general topological space, lower semi-continuous implies sequentially lower semi-continuous, but not vice versa. Okay, so anyway, we have this immediately. So assume two solutions, y1 and y2 in K. That means you have alpha equals norm of x minus y1 equals norm of x minus y2 equals inf y in K norm of x minus y. Okay, so then assume y1 not equal to y2. So let norm of y1 minus y2 be greater than epsilon, which is strictly positive. So norm of x minus y1 minus x minus y2 is equal to norm of y1 minus y2, which is bigger than epsilon, and norm of x minus y1 equals norm of x minus y2 equal to alpha. Then by uniform convexity, there exists a delta positive such that norm of x minus 1/2 y1 plus y2, which is equal to norm of x minus y1 plus x minus y2 by 2 is strictly less than alpha times 1 minus delta. In the definition of uniform convexity, we did it with alpha equal to 1. Now if you have any other alpha, it is obvious that you should scale it out. So, and this of course is strictly less than alpha. Now K is convex. So this implies that y1 plus y2 by 2 is also in K, and you have norm of x minus half y1 plus y2 is strictly less than alpha, which is the inf of overall y in K norm of x minus y, and that is a contradiction because you contradict the minimality of the K. Therefore you have only, so the assumption y1 not equal to y2 is wrong, and therefore this proves the uniqueness. Later when we do Hilbert spaces, this will be the cornerstone of the Hilbert space theory, and we will see, we will apply this there. So let us now look at an example. So in general, no uniqueness. So this y such that norm of x minus y equals inf norm of x minus z, z in K, y is called proximinal point. In the language of approximation theory, this is a very important notion. So that means the closest point. Okay, so if you look, like for instance, if you take K to be a closed convex, say a straight line in the plane, and you have a point, so this is a closed convex set, then you know that the closest point is a perpendicular projection. So this is the kind of thing which we are looking at. Okay. So now let us take V equals L to 1. That means R2 with norm 1. Okay. So this is not uniformly convex. We saw that the unit ball has several flat portions, and therefore you do not have this. So we take K equals B, closed unit ball. So we have this is B, the closed unit ball, and then so this will be the point x equals 1, y equal to 0, minus 1, 0, and then 0, minus 1, and 0, comma 1. Okay, so this will be the closed unit ball. And now we are going to take the point x to be the point 1, comma 1, which is the point here. So now let y equal to AB belong to K in the unit ball. So what is norm x minus y1? This is equal to mod 1 minus A plus mod 1 minus B, which is greater or equal to, by the triangulating, 1 minus mod A plus 1 minus mod B, which is equal to 2 minus mod A plus mod B. Mod A plus mod B is less than or equal to 1, so this is greater or equal to 1. Since mod A plus mod B is less than or equal to 1, since AB belongs to the ball. Okay. So the distance of x from B is at least 1. But what about take any point on the line? So let A plus B equal to 1, A greater or equal to 0, B greater or equal to 0. That means we are looking at this particular line, okay, here. Okay. Then what is, if y equals AB, norm of x minus y will be mod 1 minus A plus mod 1 minus B, but A and B are non-negative and sum is 1, so each of these numbers is positive. It's equal to 1 minus A plus 1 minus B, which is equal to 2 minus A plus B, which is equal to 1. Therefore, for all AB such that A plus B equal to 1, A greater or equal to 0, B greater or equal to 0. So for every point on that line, for every point in this line, we have norm of x minus y. So call this y. 1 is the minimum of norm x minus z, 1 z in B. So uncountable number of minimizing points. So you do not have uniqueness, and this is because of the lack of uniform convexity. Of course, V is reflexive, which is because it's not uniformly convex, but V is reflexive because we are in finite dimensions. That is why usually norm 1 in little l2 and little l1 will not be reflexive, but because we are in finite dimension, every space is reflexive, and therefore you have reflexive but it's not uniformly convex, therefore you do not have. So if V not reflexive, then we cannot in general guarantee existence. So there's no point talking about uniqueness. You don't even know if you have a minimum available at all. Okay, so we will wind up this chapter with this, and we will take up some exercises next time.